Okay, so this is the pre-lab for determining the chemical formula of a hydrate. Before I get started, I want to talk about hydrates for a second. This is an ionic hydrate that we're going to be studying today. It's actually copper sulfate, right? It's going to be a hydrated copper sulfate. We're going to try and determine what X is. But let's talk about the structure of ionic solids for a second. So this is a model of an ionic lattice. Hopefully in lecture you're getting into what an ionic substance is and the ionic lattice structure of ionic solids. Let's assume that these gray ones here, there are the metal cations, and the yellow we're going to call the anions, and in this case it'll be a sulfate anions. Hydrates are, well, ionic solid hydrates are ionic solids that have water spaced in between the ions, like so. Okay, so this represents a water molecule that I'm shaking right here, H2O. And there are free electrons in this oxygen. They bond in to the metal. Right? Metal has empty orbitals that these electrons bond into. And so it's really a chemical bond that these water molecules are attaching to the metal with. Now, when we heat this, the ionic solid, vibrations start. Right, heating, molecular vibrations increase, and these water molecules break off and then leave the ionic substance, right, as water vapor, steam. And that's basically the experiment that we're going to be doing today. Now, chemical formulas of hydrates. Here's an example, one I've written right here. This is copper chloride dihydrate. Copper chloride dihydrate, I've written here. This is the copper chloride portion, obviously, and this is the hydrate portion. And we call it dihydrate because there are two water molecules associated with every single formula unit of calcium chloride. Right? Now, this chemical formula can be taken as for every 1 mole of calcium, there are 2 moles of chlorine and 2 moles of water. 2 moles of water. For every formula unit of calcium chloride, there are 2 molecules of water. So this formula represents both those. For every formula unit, single formula unit of calcium chloride, there are 2 molecules of water. For every mole of calcium chloride, there are 2 moles of water. That's the chemical formula of hydrate. Now, I mentioned that we're going to do an experiment, and we're going to determine what the value of X is for our hydrate here. We don't know. Right? Calcium sulfate, X hydrate. Okay. This little dot, by the way, doesn't mean a multiplication symbol. It's just a formality representing that this is the ionic portion and this is the hydrate portion. Okay. But we're going to determine what X is in our experiment. All right, so how are we going to do that? Well, let's do an example real quick. Let's say that we have magnesium sulfate, and it's a hydrate. We don't know what X is. Now, for most hydrates, sorry, let me lock the focus here if I can. All right, good. So most hydrates, the vast majority, X is going to be a whole number. All right, it's going to be 1, 2, 3, 4, 5, 6, or 7, 8, something like that. All right, seldom is it a fraction. Fractions do exist, but in hydrates. But what you're going to be studying today, what we're doing with the copper sulfate, X is going to be a whole number. So X is going to be a whole number. In this example here, magnesium sulfate hydrate. We've got to find out what X is. So we heat this. Write a chemical equation here showing that we're heating it. And we drive off all the water. All this water is broken out of the hydrate. So over here, we get the anhydrate. The anhydrate plus X moles of water. Right, so this is the chemical equation. The molecular formula, the molar mass of magnesium sulfate is 120.37 grams per mole. We need that information. And for water, it is 18.015 grams per mole. 0.015 grams per mole. So let's suppose that we start off with 3 grams of the hydrate. 3 grams of the hydrate. Now we heat it, dry off the water, and then we weigh the anhydrate. Let's say after we do the experiment, we weigh the anhydrate and we're left with 1.47 grams. 1.47 grams of the anhydrate. Well, how much water was lost? Mass has to be conserved. If there are 3 grams over here on the reactant side, there've got to be 3 grams over here on the product side. So just 3.00 minus 1.47 must be the mass for the water. So 1.53 grams of water. That's how much was lost. All right, so we have the mass of the anhydrate. We have the molar mass of the anhydrate. We can calculate the number of moles of anhydrate we have after the experiment. We can also do the same for water. We can determine the number of moles of water that was lost. So let's do that real quick. For water, 1.53 grams of water. For every 1 mole of water, there are 18.015 grams of water. Units cancel. And that's going to give us 0.0849 moles of water. That's how many moles of water containing this 1.53 grams. How many moles of the anhydrate do we have? Same calculation. 1.47 grams of the anhydrate times, for every mole of the anhydrate, there are 120.37 grams of the anhydrate. That gives us 0.0122 moles of the anhydrate. Okay. Now that's significant figures here. I'm limited to 3 because my mass over here is limited to 3, because I started here with just 3. Doing the subtraction, I can only have 2 decimal places over here, which gives me 3 significant figures. Limited 3 significant figures here, so I'm limited to 3 significant figures over here, my calculation. Okay, so what do we do with these 2 values? Well, look back up here at the chemical formula. For every 1 mole of the magnesium sulfate, there are X moles of water. So in essence, there are X moles of water for every 1 mole of magnesium sulfate. Okay. Well, that has to equal the ratio of these two. 0.0849 moles of water That turns out to be, with significant figures, 6.96. Okay, 6.96. But remember I said X has to be a whole number, right? So this value over here is associated with our limits in measurement, okay? So we're not going to come out to exactly 7, but you're going to get some number that's going to be close to a whole number after the experiment. So in this case, doing this experiment, X turns out to be 7. So now we've determined the chemical formula of our hydrate. It's MgSO4.7H2O. Okay. Now I mentioned you're going to do the same experiment with copper sulfate. Right? Copper sulfate. So you're going to have to determine the molar mass of the anhydrate for copper sulfate. All right, so CuSO4, you're going to need that value just like we needed the value of the molar mass of magnesium sulfate. Okay. So you're going to need that value for your experiment, so make sure that you do that. Details of the experiment. So we're going to take this. This is an Erlenmeyer flask. It's a 50 milliliter Erlenmeyer flask. 50 milliliter. So I'm going to weigh this flask in the experiment. I'm going to weigh it, get the mass of the flask. Then I'm going to add copper sulfate to the flask. Then I'm going to weigh the flask with the copper sulfate in it. And taking the difference of those two, I can get the mass of the copper sulfate hydrate I've added to the flask. Then I'm going to take the flask that has the copper sulfate hydrate, I'm going to put it on a hot plate, and I'm going to cook the heck out of it. All right, hot plate, I'm going to have a dial setting of 10, as hot as the hot plate can go. And I'm going to let it sit on the hot plate for about 30 minutes. 30 minutes. I'm going to take it off, let it cool to room temperature. Then I'm going to weigh the flask that now has the anhydrate in it. I'll get the mass of the flask and the anhydrate. And from that, I can determine the mass of the anhydrate. And I can also determine the mass of the water that was lost. Okay? I'll get these two values. And then you can do the calculation. All right? Now, during the experiment, I'm showing you, I'm not going to be talking a whole lot. All right? I'm not going to be providing a lot of guidance. I'm just going to be doing the experiment and showing you values. Okay? So make sure you take good notes. Of course, this is going to be on a video, so you can stop, pause, go back. But again, I'm not going to give you much guidance during the video on the experiment. All right, with that said, I guess we'll go ahead and get started. Oh, one other thing. I need to mention something. I've done this experiment a lot with students, and there is a common mistake, and I want to point out the mistake to you. It's easy during the experiment to get these two values mixed up. In other words, what you think is the mass of the water is really the mass of the anhydrate, and vice versa. And if you do that, you're going to get some wonky numbers, right? You're going to get numbers where the x is too high. So make sure that you have the mass of the water and the mass of the hydrate, and you haven't switched those two values. Okay, that's all I have. So let's get busy with the experiment.